So now, the problem, one of the things in the body is that hydrophilic, hydrophobic discussion. Hydro means water, philic means loving, phobic means fearing. How a molecule behaves in a water environment is fundamental since we are so much of water. Think of oil and vinegar. Some of the stuff combines with the water, the vinegar, but then other molecules, they separate out. That would be the oil. What makes a molecule hydrophilic? The ratio of hydrogen and oxygen in water is H2O. That means 2 to 1 as a ratio. If we look back at the sugar, we have, on every carbon, we basically have hydrogens going up and oxygen and hydrogen, hydroxyl and hydrogen ion. That's a water thing. That ratio throughout the whole molecule is a 2 to 1 ratio. That's like water. Therefore, it likes to be in the water. If that ratio is not the same, then it will be separating out in water. And that will be our oil. So from the food's perspective, protein and carbohydrates, both of them, are hydrophilic. I gave you a few good carbs here in case you want to know about good carbs and bad carbs, since you probably already know all that. But some people, I'm surprised, sometimes we don't. Green vegetables is the same sort of thing as bread. It's carbohydrates. And sort of where things go awry sometimes when people don't know that a vegetable is actually carbohydrate. But it is. So since glucose is the universal fuel, it is good for the body to store some of that for quick energy. Liver and muscle mainly store long chains of glucose. The brain has some, a little bit. But the textbook sort of, I got that in some articles, not in the textbook. What are those molecules called? Anybody back there? Or back there? Just not the front right. Anybody?
Glycogen.
Glycogen, there you go. So, in a plant, we have cellulose. You can't do too much of that. It's fiber stuff for us. But in the animal, we have glycogen as a long sugar chain. And when you think about the muscle, I was just doing the questions on the muscle. When we look at the muscle energy, we need to use a lot of energy in the muscle, maybe run, or just from standing and holding up. So having glycogen storage in the muscle makes a lot of sense.
Don't they say when marathoners bonk, it's because they run out of glycogen?
Oh, is that right? Yeah, I could see that. That's a big shift. And then the other, the liver does everything. The liver is like this universal processing plant that does a whole bunch of stuff. So if we got glycogen in the liver and our blood glucose goes down, the sugar in the blood, we can chop them up and raise the glucose level up a little bit before we can eat something. So that's why that's also good to have it in the liver. So those are those two places. But if you notice, is that the next question?
Yes.
That's a long question. If you notice, a lot of people these days deal with overweightness. That probably is not even good. There are reasons for that, and some of them are found in the food manufacturing industry. So first, the food people started trying to make so we don't have, the food doesn't spoil. That was about 100 years ago. But that also brought with it the destruction of the natural food stuff. And so now we have Cheetos. And we call it food. I mean, we have lemon polish for our furniture top things that is real lemon, and in the lemonade we have fake lemon to drink. I mean, however, vinegar got a table more important than a person. I don't really know. But we have to be a little bit educated on some of this stuff. Because food manipulation is a big deal, and it can be a deadly industry. A lot more people these days seem to have heart attacks. Has to do with food. At least some of it. Our brains are quite easily manipulated, especially with the overwhelming bombardment of commercials, subliminal messages, blah, blah, blah. One of the wrong concepts is that fat in food makes you fat. The problem is the body needs quite a bit of fat. The brain, for example, is mostly fat. Fat's what satisfies you or me when we eat it, which means we don't have to eat that much. But we eat more if we don't eat fat. If we just use sugar, we eat fat-free foods, we eat more of the food. What happens to the body? What does the body do with the excess sugar? Turns it into fat. So that's where the pathway is. So that's where we have to change our brain around. And no, fat is good. It just depends on fat. We'll talk about what fat. And avocado is just fat. Carbs are broken down by the digestive system. The monosaccharides absorb into the bloodstream. From there, the glucose needs to enter cells. Insulin is a hormone from the pancreas. Did you know that? Insulin comes from the pancreas, which then alters protein channels. So in the cell, in like a muscle cell, let's say, that contracts, you have a cell membrane that surrounds it, so the cell is by itself. We talked about that. We need a boundaries. It's very important to maintain life. It's a boundary. So the insulin opens a channel in the cell that lets the glucose in. It's a protein channel that's like a round thing, and if it's squeezed, it's closed. And if there is insulin on it, and it says, talks to the set thing, the protein, it opens and it's a channel just for glucose. And it lets the glucose into the cell. And what that does, the glucose then can go in and make energy. I mean, the cell can make energy out of the glucose. The problem is that the blood sugar makes blood sticky. So if we eat something and we have sugar going into the blood, it makes the blood sticky. So we want that insulin to pick up that stickiness fast and get rid of that glucose and put it in. But that sticky blood can be damaging to the body as it gets clogged in small arteries and can make you sick. If we eat food that enters the blood quickly, the pancreas needs to respond and work overtime to release insulin all the time, very quickly. So we have created something to measure that. Because when the pancreas works overtime, it makes it tired, and at some point it becomes inefficient. The insulin is not there all the time when we need it. And that's called insulin insufficiency. And we can develop diabetes. And in this, we have a lot of this type 2 diabetes that is often manageable, but we don't have the system doesn't give us necessarily the education. And so what I want to ask you is, what is the glycemic index? What does the glycemic index describe? Anybody?
Does it measure how fast it takes sugar to reach the bloodstream?
That's right.
Yeah.
The glycemic index measures how fast. Do I have one here? It measures how fast the sugar goes into the bloodstream. And you can have whole lists. It's just an index from 0 to 100. And 100 is table sugar. So if you eat table sugar, how fast is it going to the cell? And that's what that measures. I think we have like one here. See, like there's potato, there's maltose, there's carrots, there's all kind of stuff. I know it's a little...
Those are the ones that enter the bloodstream.
The 110, 100 is glucose. The higher the number, the faster it goes into the bloodstream. The lower the number, like peanuts, the slower it goes to the bloodstream. And so it balances that. So the insulin read is not as fast as grain. Huh?
And fat slows everything down.
Oh, that's right. So does that make sense? So if you have a problem with sugary stuff, looking at having a glycemic index is kind of good, because you can go shopping and you kind of see, oh, look at that, maybe that's a little better this time or something. But I like this. When you look at good carbs and bad carbs, you can see, like, you know, how fast does the sugar go into the system? Let's say you eat a donut. You're a policeman, you go eat the donut and have a coffee, right? Dunkin' Donut. And the sugar Is that something bad to say? Is it? But they always do that. Why is anything that's true bad to say? This is California again, right? So the sugar goes up real fast, and guess what? We let insulin go into the system a lot and fast, and we take all the sugar out, a lot of it. Bam! Then you undershoot it, and you don't have any sugar. Guess what that is? You're really hungry at 11 o'clock.
And doesn't that like drain you?
Yeah.
You get that rush from the sugar.
And you know the problem, and then you go have lunch, and let's have lunch. We go have McDonald's and a Coke, because then we do the same thing again, and by 2 we go like, huh? What am I supposed to do? I'm working. And that means, because what happens is the brain doesn't have receptors, or not that many receptors for the glucose to go in. So you rush, all the sugar rushes out of the blood into cells, but not the brain cells. And so the brain is starving for sugar. Doesn't have any food. And so the problem here, we can take this now for one more step. Then when you're down here, your hypothalamus in the brain says, oh my God, I'm hungry, I need to have something real fast now. A candy bar. That's great, because it gets it in real fast, and I have energy. So if we want to lose weight, for example, and we don't eat breakfast, how many of us want to lose weight, don't eat breakfast? I mean, I used to do that all the time. I'm like, oh, the less I eat, the better. But then by noon, it's like, I'm hungry. I eat whatever. I used to be chubby. And then you eat, and then your brain decides, your hormones decide what you eat. It's not your willpower that's crappy. It's your hormones that you don't work with. And so what is much better is if you eat a good hearty breakfast. And good hearty breakfast means protein.
And white?
Yeah, that's perfect. But oatmeal? Oatmeal, that's even better.
Breakfast of champions.
The genes are fine, but they're not a substitute for doing things right for the body. And that's right, we do have an obligation as humans to treat our body well. I mean, you can treat it like shit, but then they're all of it. So the whole society suffers on that, because who pays the medical bills? Everybody. At the end of the day. So there is that sort of need. So that's a very, very good question. I like the hereditary unless it's a cop-out. Lipids. I don't know if there's a question on lipids. Is there a question on lipids? Neutral fats. The ones we eat the most of are known as triglycerides. Tri means 3. So there's going to be something that has to do with 3 in this molecule. Chemically, they look like the letter E. So that is 3 chains of carbons, like 1 carbon chain derives from what we call a glycerol backbone. That's just this part of the E. We don't worry about detailed chemical mass. I don't bring this back as a term. The carbons on the chain are covalently bonded. When all the connections are single bonds, which means the molecule can freely rotate around itself, it arranges itself that it's as compact as possible. And the carbon chains arrange parallel, and they pack tightly. That structure will be solid at room temperature. A good example of that is butter. How do oils differ?
They don't.
They're liquid. Uh-huh.
They don't solidify at room temperature, oils?
They're liquid, right?
Yeah.
But why? Does anybody know why?
Yeah.
Good. Some of the chain is unsaturated. So when we look at butter, and this discussion brings me to the trans fat, so hold in there for a second. When we look at butter, we have all the things are single bonds, so they're all nice and straight. When we look at fat oils, like olive oil, there's a kinks in it. When we talk about omega-3s, omega-6 fatty acids, and that sort of stuff, we're talking about where is the kink, actually. The omega is from the back, we count each how many bonds, and then there's the kink. So,
Is it a kink because it's not a single bond?
yes. The kink is, it cannot rotate. The molecule is stiff. Once it's stiff, it cannot rotate. And then there's 2 configuration chems. They call them cis and trans. We don't worry about that. But the way that the configuration is, then is important of, is it bioavailable for the body or is it not? And that's part of where then problematic things come in with trans fats. That's part of the problem.